Welcome and thank you for standing by. At this time, all participants are in a listen-only mode until the question and answer session of today's conference. At that time, you may press star 1 on your phone to ask a question. Today's call is being recorded. If you have any objections, you may disconnect at this time. I would now like to turn the conference over to Nancy Jones. Thank you. You may begin.
Thank you, operator. Hello, everyone. I'm Nancy Neal Jones from the Office of Communications at NASA's Goddard Space Flight Center. Before we begin today's briefing, we're going to start with a short video.
As we started to approach Bennu from a distance and it started to fill up the camera field of view, it looked exactly like we thought it would, with a few boulders sticking out. But as we got closer, we expected to see a very sandy surface with maybe a few boulders here and there. And what we saw is very little sand. And we saw these mountains, we saw boulders, we saw rocks, and we saw very few areas that had this sandy surface that we were expecting and what we had designed to.
We have never done this before. We're actually going to collect a sample and bring it back down to Earth for further examination by scientists.
In order to achieve that objective, the OSIRIS-REx spacecraft has been navigating around Bennu for about the last 2 years, studying it in great detail, and also overcoming a number of challenges that Bennu has presented. We were looking for locations on Bennu that were 50 meters in diameter, relatively flat, and covered with fine-grained material. And by fine-grained material, I mean stuff that's the size of a dime or smaller. We realized that there were no sites on Bennu that even came close to meeting this criteria. Everywhere we looked was too small and covered with boulders. So we actually had to fly a number of additional close passes over the asteroid and rethink our entire plan for grabbing the sample.
As we started to approach Bennu from a distance, and
We are 1 day away from NASA's first attempt to collect a sample from the surface of asteroid Bennu. Tomorrow, the OSIRIS-REx spacecraft will conduct its touch-and-go maneuver, also known as TAG. During this event, the sampling mechanism will touch Bennu's surface for several seconds, fire a charge of pressurized nitrogen gas to disturb the surface, and collect a sample before the spacecraft slowly backs away. To tell us more about this U.S. history-making event, we have with us today Thomas Zurbuchen, Associate Administrator, Science Mission Directorate, NASA Headquarters. Lori Glaze, Planetary Science Division Director, NASA Headquarters. Heather Enos, OSIRIS-REx Deputy Principal Investigator, University of Arizona. Kenneth Getzendanner, OSIRIS-REx Flight Dynamics Manager, NASA. And Beth Buck, OSIRIS-REx Mission Operations Program Manager, Lockheed Martin Space. Get to know the team members involved in this telecon by visiting NASA on Facebook and Twitter to watch short videos about OSIRIS-REx's journey to Bennu and back. Now we'll start today's briefing with a few words from Thomas.
What an exciting time, and walking up and down the hallways here, what an exciting, just entire kind of emotional state this team is in. You know, it feels like something really amazing is about to happen tomorrow, and I just couldn't be more excited to be part of this team and just be part of this amazing event. Of course, this all started something like September 8th, 2016, when a United Launch Alliance Atlas V lifted into the sky, and long before that, where this mission was put together. This is a historic first mission for NASA, returning an asteroid sample, and it is hard. It is hard, even without COVID, but COVID made it even harder. There's so many things that need to be resolved, and it is, like all science that really matters, a true teamwork. And with this, I just want to point you to look at Sierra Gonzalez there, at the bottom right here, Lockheed Martin Systems Engineer, just one of the many team members who are making this possible. This photo was taken on April 14th during a 4-hour rehearsal of the checkpoint maneuver when OSIRIS-REx came within 65 meters or 213 feet to the Bennu surface. And that's just an amazing step, one of many that got us ready to today. OSIRIS is one of many who are working to make this mission happen. And I really want to thank the teams, both at the University of Arizona, Goddard Space Flight Center, Lockheed Martin, of course, and the many other companies and scientists and so forth who are really at the heart of this team. OSIRIS-REx is a mission of international partnership with the Canadian Space Agency, who provided the laser altimeter, which is a really critical component, of course, and then also with the Japanese Space Agency, JAXA, with whom we're sharing samples and also get samples from Hayabusa 2 that are currently on the way back from Ryugu. Together, by sharing these, we maximize the science that comes from it to the benefit of the entire international community. So when you think of BANU, you think of it as a really almost a Rosetta Stone, something that's out there and tells the history of our entire Earth, of the solar system during the last billions of years, and the violent evolution of that history as well. We didn't even know that BANU existed until it was discovered in 1999, actually via a telescope of NASA's Near-Earth Object Observation Program. And the OSIRIS-REx spacecraft, of course, is just about the size of a 15-passenger van, and it is going to sample the Nightingale site. And if you think about it, that's about 8 meters in diameter, and in an overall crater that's about the size of a tennis court. So think of this kind of coming from deep space onto this rotating object, really hitting that spot. So as I said, the challenges are big, but I think the team is ready. You see there in the middle a cropped image that shows you kind of the size scale and the overall, overlaid with the OSIRIS-REx spacecraft to illustrate the scales that I just described in words. Well, BANU presented a lot of challenges. It's not the sandy beach we all hoped we would see initially, and I just want to tell you, exploration and surprise have a lot in common, and this is no exception. And of course, the team was up for it. It's through the incredible ingenuity of the team that enabled us to get where we are, and also will enable what will happen tomorrow. Of course, sampling requires incredible engineering, such as the autonomous navigation system. We're going to hear about that from one of the panelists here, and also the mapping, which was so critical to actually know where we're heading. So, of course, we also learned, and yet in another surprise, that BANU is active and is emitting softball-sized, objects into space. One thing that none of us were really thinking about before. Again, we love being ready for this, and I just look forward to the other panelists' comments here, starting with Dr. Lori Glaze, who is the Planetary Division Director. Lori.
Thank you so much, Thomas. I'd also just like to take a moment and really thank the team. This is just an amazing mission, incredible mission, and I'm so proud of all they've achieved. Even under great circumstances, it's been a lot to achieve, and under the adverse conditions we've all been working under, they've really done an amazing job to keep everything moving forward in these unprecedented times. BANU is one of over 1 million known asteroids in our solar system. And these asteroids are really relics of that earliest material that formed the planets in the solar system, and they hold the key information to unlocking our understanding of how the solar system formed and how it evolved over time. Missions like OSIRIS-REx, which is shown in the middle part of the graphic here, Psyche, which is shown on the lower right, Lucy, which is shown in the middle on the lower part of the panel, New Horizons, not shown here, but is out exploring the outer extremes of the Kuiper Belt, and DART, which is shown in the lower left part of the panel. All of these missions address major components of asteroid science, as well as advancing NASA's planetary defense efforts to better prepare us for how to respond to asteroids that may threaten Earth in the future. The returned samples from BANU could help us answer some key astrobiology questions, such as how water and organic material were delivered to Earth and the role those key ingredients have played in the early initiation of life on Earth. And this type of sample return is really an important strategy for NASA, and particularly for planetary science. From the Apollo lunar samples that are shown on the top left of this graphic, where we just recently, just over the last year, opened up a sealed sample that was collected by Apollo 17 almost 50 years ago, and it was preserved and just opened, this pristine sample. These important samples from the Apollo era and now all the way through to OSIRIS-REx, and then ultimately in the coming years, the eventual return of samples from Mars. All of this is really important. All of this sample science is so important because back on Earth, we can apply the full breadth of the terrestrial science laboratory capabilities that we have to study the physical and the chemical characteristics of these pristine, unaltered materials in our state-of-the-art laboratories. With Bennu specifically, we'll be able to do so within the context of the remotely sensed data obtained while the spacecraft was orbiting Bennu. And the samples returned by Bennu will also allow our future planetary scientists to ask questions we can't even think of today using analysis techniques not yet invented, and help inspire the next generation of explorers. So with that, I'm so excited about the TAG event tomorrow. We're at T-1, and I want to pass it over to Heather Enos, who is the Deputy Principal Investigator for OSIRIS-REx. She's going to talk a little bit about how the team selected Bennu as its target and what they hope to learn from this mission.
Great. Thank you, Lori. I'm incredibly excited. I've been working on this mission for about 12 years to the date, which is a long part of my life, and it's definitely a great capstone. Planning a complex mission requires planning for the known and the unknown, and as we've heard both from Lori and Thomas, we have had a little bit of both on this journey. And as Lori indicated, we have nearly 1 million asteroids we could have selected as our target asteroid. So one would ask, out of the hundreds of thousands of options, why did Bennu get to be the lucky candidate? Well, it turns out there's 3 major criteria that we needed to consider. And proximity to Earth and accessibility are really important. We need to be able to get there and back in a reasonable amount of time. And the size is also very important. We needed something that was at least 200 meters in diameter, and fortunately, Bennu is about 500 meters in diameter. And this is really important because it's not easy to navigate around a small body and ultimately get to the surface. And fortunately, we have a great flight dynamics team, and Kenny's going to explain to you just exactly how we are doing that tomorrow at Bennu. We also focused on the composition and the science value associated with our choices. And we wanted a pristine, carbon-rich asteroid that would unlock clues to the formation of the solar system and Earth and life as we know it today. And we do have good ground-based evidence that Bennu is a carbon-rich asteroid, so it became our choice for sample collection tomorrow. Next slide, please. Another significant part of planning was we needed to select the science instruments that would allow us to characterize the geography and composition of Bennu and find the optimal site for collecting a sample. Well, I am really proud to say we not only chose a really great asteroid, we brought along the instruments necessary to really understand the surface of this asteroid and led us to our sample site collection of Nightingale. We have great instruments on the spacecraft, and I'd like to introduce them for just a moment because they have done a tremendous job. We have the OCAMS instrument, which actually is 3 cameras that were built by the University of Arizona. The OCAMS instrument has been very, very instrumental in taking images at high resolutions of the entire surface of Bennu down to the centimeter level. We also have 2 spectrometers that are also very instrumental in mapping the mineral and chemical composition of the surface. We have an infrared spectrometer, which is OSIRIS, that was built by our partners at Goddard Space Flight Center, and we have a thermal emission spectrometer that was built by our partners at Arizona State University. We also have a laser altimeter that is provided by the Canadian Space Agency, and it has mapped the topography at the 5-centimeter scale of the entire surface of Bennu, which is just remarkable, amazing results. We also have a student experiment, which has also been a lot of fun to take the next generation along with us on the journey as well. And it's an X-ray spectrometer that was built by a team of students at MIT and Harvard. So since we arrived at Bennu in 2018, we've put these instruments to work a lot. We have done a significant amount of observations at the surface. And as a result, we have widespread evidence that Bennu does in fact contain carbon-rich material and water-bearing minerals. So Bennu definitely answered the mail for us. We chose the right asteroid, and this is exactly the kind of material we want to bring back to Earth and further analyze in our laboratories for multiple generations to come. But then there was the unexpected surprise that we've all been talking about, the rough, rugged surface. We didn't find smooth surfaces with lots of large hazard-free areas. So that's when it comes down to the next very important component of planning ahead. And that was during planning ahead, not only did we pick a great asteroid and the perfect instruments, we actually put together the perfect team. And that's what is important for solving the unknowns and finding solutions to the challenges that you don't necessarily expect. So during this time, we really put our heads together. We are a very tightly integrated team. In terms of the way OSIRIS-REx works, the relationship between science and engineering is actually very seamless, and we depend on each other on a very regular basis, in addition to our mission operations part of the team. So we sharpened our pencils to find a solution to this challenge. And so Kenny's going to elaborate just on how we refined our capabilities to ensure we can safely deliver our spacecraft to the surface. Next, please. So during our first year at the asteroid, we carefully imaged the surface, and we were on a hunt for the exact place that we were going to get our precious sample to return to Earth. So given that we had solved our problem of not being able to meet our requirement of a large sandy beach, or Bennu, in fact, didn't meet our requirement, we had successfully found a solution to safely deliver to multiple sites, multiple candidate sites. So our driver then really became which site has the higher abundance of fine-grained material. And by that, I mean fine-grained material that is 2 centimeters or less in size. And Beth is going to talk about why that was so important, because our tag SAM head has a constraint of ingesting material up to 2 centimeters in size. So at this point, the team, which included several students, poured through thousands, and I mean thousands of images, and counted thousands of rocks to estimate the amount of fine-grained material at both candidate sites. But at the end of the day, Nightingale was our winner, and that's where we're going tomorrow. So although it does have some hazards, and the safety and deliverability analysis meet our requirements, we are quite confident we will safely touch the surface tomorrow as we approach Nightingale's crater. It is the site with the highest probability of providing fine-grained material with at least 50 grams of collection, as well as its science value is outstanding. It's a young, fresh, pristine crater with the presence of organics. So I really am, and the entire team is really excited to touch the surface of Nightingale tomorrow and collect a bounty of that precious sample we're so anxious to bring back to Earth in 2023. Now, Kenny, over to you.
All right, thank you, Heather. Excitement, we've heard it from a few different people on this panel. That is certainly the word to use to describe today. For the entire team, but particularly for the navigation team. And I'm very proud to be a member of that team, and we've done some incredible things. Since arriving at Bennu 2 years ago, the team has certainly learned a vast amount about our asteroid, and just as importantly, how to navigate and operate within its unique small body environment. Over the course of the mission, the navigation and spacecraft operations teams working very closely together have designed and executed 115 separate maneuvers and generated 291 trajectory solutions and onboard ephemeris updates. Because of Bennu's relatively small size and weak gravitational attraction, burns to significantly alter the spacecraft's trajectory or even completely reverse direction entirely in some cases, as you can see from the video, are relatively small in magnitude, typically with delta V's on the order of a few centimeters per second or less. In fact, our most recent burn, performed just last Saturday to fine-tune the departure point for TAG, was a mere 0.5 millimeter per second in magnitude. However, because of the light time delay and precision required, we aren't able to, quote, joystick the spacecraft in real time. Instead, each maneuver requires careful design and planning weeks ahead of time, with a final opportunity to tweak the design roughly 24 hours prior to execution. Advance to the next graphic, please. All of these maneuvers were necessary to steer OSIRIS-REx above and around Bennu with various reconnaissance passes and orbits at distances ranging from a few kilometers down to hundreds of meters above the surface. This incremental and methodical approach gave us confidence that we were able and ready to make the next step closer to the surface, while collecting valuable science and engineering data along the way. Ultimately, we collected all of the information necessary to select a tag site and collect the sample. During our last tag rehearsal in August, the spacecraft descended down to approximately 40 meters above the Nightingale crater before safely backing away. And with the completion of that last rehearsal, we are now ready to take on tag. If you could please play the next video. Thank you. As Heather mentioned, characterizing Bennu's physical characteristics and dynamical environment is essential to navigating the spacecraft accurately and precisely. The navigation team worked closely with the scientists, so thank you, Heather, and your team, to determine Bennu's mass, gravity field, spin state, and various other physical characteristics used to model and predict OSIRIS-REx's motion about the asteroid. A key data product for navigation was a high-fidelity model of Bennu's shape and topography, which is used in combination with dedicated optical navigation images to determine where OSIRIS-REx is relative to Bennu's surface at any particular time. We've navigated with those topographic maps since early in ProxOps and continuously iterated with scientists to make improvements and increase the resolution as the data became available. Those maps are also key in guiding the spacecraft down to the surface for tag, as we'll hear more about in a moment. The navigation team also had to understand and characterize other forces acting on the spacecraft besides Bennu's gravitational pull, including solar radiation pressure from the sun, as well as thermal radiation forces emanating from the spacecraft itself. Precise modeling and calibration ultimately led to the navigation team's ability to predict OSIRIS-REx's trajectory forward in time to unprecedented levels. During the rehearsals and reconnaissance passes, the team was able to predict out the spacecraft's departure point 32 hours in advance down to an accuracy of a few meters, which is an essential for accurate and successful tag execution. If you could please play the next video. In about 22 hours from now, the spacecraft will execute a series of 3 maneuvers that will take it out of orbit and slowly touch down inside of Nightingale crater. The spacecraft starts out in roughly the same 900-meter orbit it's been in for the past 8 weeks. Over the last 2 weeks, the team has executed 4 trim and phasing maneuvers to slightly tweak the orbit and ensure the spacecraft is as close to the desired departure point as possible. The first maneuver, the Orbit Departure Maneuver, or ODM, will occur at approximately 1:30 p.m. Eastern tomorrow, when the spacecraft is about 1 kilometer from the center of Bennu and on the other side of Bennu from Nightingale. The 8 centimeter per second burn kicks OSIRIS-REx out of orbit and initiates a 4-hour journey across Bennu and down to about 100 meters above the tag site. At that point, the checkpoint maneuver turns the spacecraft and sends OSIRIS-REx down towards the surface. After the spacecraft crosses about 50 meters in altitude, about 10 minutes after checkpoint, the third and final maneuver, the matchpoint maneuver, slows the descent to a mere 10 centimeters per second and sets up the spacecraft for soft contact on Nightingale. If you could please play the next video. While the tag trajectory is designed to touch right on the precise tag site, that Heather and company worked so hard to determine. Small errors in maneuver execution and models move OSIRIS-REx slightly off course during the descent. The original tag accuracy requirement was to touch down within 25 meters of the desired sample location. However, as we've already heard, Bennu's rough surface and potential hazards mean our performance has to be much better than that. Just prior to checkpoint, the onboard guidance system Natural Feature Tracking, or NFT, tweaks the checkpoint and matchpoint burns to correct any errors and target the tag site. We'll hear more about that, about NFT from Beth in a moment. Combining NFT with our enhanced navigation modeling means we now expect to land within 7 meters of the desired tag site at touchdown, an improvement of over a factor of 3 from the original requirement. Please play the next video. As we speak, the navigation team is in the middle of a final 24-hour late-date design for TAG. Earlier this morning, the spacecraft downlinked a set of optical navigation images taken within the last 24 hours. These images were then processed by the OutNav team using detailed topographic maps to produce measurements used in the orbit determination process. The orbit determination team combines those measurements with radio tracking data and our precise models of the spacecraft's motion to estimate a best fit trajectory and update our knowledge of where the spacecraft will be at the time of tomorrow's ODM. The maneuver team is currently using that updated trajectory to slightly tweak the tag maneuver designs and NFT products to ensure we get as close to the tag site as possible. Any moment now, the navigation team will deliver those products to the spacecraft team, who will build, test, and uplink the final commands to OSIRIS-REx. And with that, I'll hand it over to Beth Buck, OSIRIS-REx's Missions Operations Program Manager.
Thanks, Kenny. So today the team will be using this final navigation design update to build the spacecraft products that will autonomously guide OSIRIS-REx to Bennu and tag and back away. These products are being built, tested, and reviewed this evening, and then once approved, they'll be uplinked and commanded to the spacecraft tomorrow, Tuesday morning. Then Tuesday, the team will be on their stations in the mission support area right here at Lockheed Martin in Littleton, Colorado, starting at 6 a.m. Mountain Time. The ACE will radiate the final parameters to the spacecraft at about 7:15 a.m. Mountain Time, and then the spacecraft has what it needs for this autonomous operation. So the events we received data for the rest of the day, I'll be referencing in Earth receive time. That's currently about 18.5 minutes behind the events on the spacecraft due to one-way light time from Bennu, which means the data we receive or send takes that long to get here due to the distance Bennu is from Earth. If you could please play my second video. So at approximately 11:50 Mountain Time, we'll perform the orbit departure burn to head in towards Bennu, and we'll extend the arm with the sample head. Just over a half hour before tag, we will move the solar arrays to a configuration to help protect them better. At 3:50 Mountain Time, we'll complete the checkpoint burn, and about 10 minutes later at 4 o'clock, we'll complete the match point burn, and then plan to tag the asteroid about 10 minutes later at 4:12 p.m. Mountain Time, and then we'll quickly back away. Because of our orientation, we'll be on low-rate data for communications, so it won't be till later Tuesday evening that we are oriented to enable high-rate data communications, and that's when we'll start to get the imagery and other spacecraft data. Please play my third video. Due to the low gravity, we can't actually land on the surface of Bennu, so we will only be kissing the surface with a short touch and go measured in just seconds. We have a Lockheed Martin designed sample head that will make contact with the surface and actually compress down on it while blowing compressed nitrogen gas to further stir up the surface and collect the fine-grained regolith material into the touch and go sample acquisition mechanism, or what we call TAG-SAM. It's acting like a reverse vacuum cleaner and looks much like an older car air filter. That TAG-SAM can ingest particles about 2 centimeters or less in diameter or smaller than a nickel. So after 6 to 16 seconds of contact on the surface of Bennu, we will then slowly back away from the asteroid. This sample head will later be stowed in the sample return capsule, where it'll stay for its trip back to Earth. Just that sample return capsule will be returned to the desert of Utah in about 3 years on September 24th, 2023. So this team has faced a lot of challenges that several of us have addressed, and they continue to overcome those. One of those was obviously tied to the asteroid itself. That was a much more rocky surface and no large boulder-free areas, as we mentioned. Fortunately, during the design phase, Lockheed Martin developed a backup capability to use as an optical navigation system. It's called natural feature tracking. At the time, there was actually a concern as to whether there would be enough natural features on Bennu to use landmarks for an onboard optical use. But Bennu turned out as it did, and which turns out with natural feature tracking was a much better way to come into the tag site than the originally planned LiDAR. If you can start my fourth video, please. So tomorrow, we'll be taking a series of images as we approach Bennu that are compared to the onboard image catalog that was created through the mapping phase of Bennu that we performed over the last 2 years. That will be used to determine where we are, matching these images to those that were previously logged and cataloged to see if we are heading in as planned to that small sample site on Nightingale. Start my fifth video. We need this precision because we are coming into a very small area. It's just 26 foot wide, and we're 200,000 million miles away. We want the best chance of obtaining the sample and to protect the spacecraft. So as long as we are looking good, we'll continue to proceed to touch that asteroid, but the spacecraft will also be using these images to determine if it should back away sooner and actually abort the tag attempt. My sixth video, please. While we're planning for success tomorrow, there's the real, albeit small chance that the spacecraft could wave off the attempt if the onboard computing determines, based upon the imagery fed into natural feature tracking, that the trajectory puts us at risks of hazard since Bennu is so rocky. There are different points this is determined, and we could abort the tag attempt starting at about 125 meters above the surface and as late as 5 meters above the surface. The mission's calculated that there's less than 6% chance of a wave-off during tomorrow's attempt, but this wave-off is designed to protect the spacecraft and would enable us to then try an additional tag attempt at a later date. Since it's more likely that if we had to abort, it would be at the 5-meter point, we will have disturbed the surface there with our thrusters, and thus our natural features that we've mapped will also be disturbed. So our next attempt for tag would most likely be at the backup site of OSIRIS once we've assured the spacecraft is healthy. Let me start my final seventh video. But since an abort is very low probability and the spacecraft continues to perform so well, we are planning and looking forward to actually tagging tomorrow, October 20th, 2020. It's the event the full team has been working so hard to prepare for years, and we are really excited to have it nearly upon us. And back to you, Nancy.
Operator, we're now ready to take questions from the media.
Thank you. We will now begin the question and answer session. If you would like to ask a question, please press star 1, unmute your phone, and record your name and affiliation. If you need to withdraw your question, please press star 2. Again, to ask a question, please press star 1. Our first question comes from Elizabeth Howe with space.com. Go ahead, your line is now open.
Hello, and good luck with tomorrow. Thanks for taking my question. I think this would probably be for Kenneth or for Beth. Can you let me know when we will start to have a feeling of success or failure for the spacecraft, what kind of data you will be looking for, and when that information approximately would be appearing?
We'll start to get some of the high rate data Tuesday night, which will start to give us a little better indication of how the spacecraft is, but we won't have imagery down until our first imagery will start coming in on Wednesday, and that will give us a much better feel for whether we have a sample or not and how the spacecraft is actually performing. But we'll continue to analyze that over the next 10 days or so with that, too, as we proceed forward.
We're ready for our next question.
Our next question comes from Eric Berger with Ars Technica. Go ahead, your line is now open.
Hi, this is Eric Berger with Ars Technica. So just to follow up on that question, we will not know Tuesday evening whether this was a success or not. And then secondly, could someone talk about kind of how the data or sample that you're collecting with this mission will complement or is different from Hayabusa 2? How basically those two samples might sort of better give us more information about the solar system's history. Thank you.
So just to confirm the first part, that's correct. We will know if we've touched the asteroid, but we will not know if we have a sample yet tomorrow.
Right, and this is Lori Glaze, and so in response to the second part of your question about Hayabusa 2, so we're collaborating very closely with the Hayabusa 2 team. We have exchange of scientists working on both missions, and of course we'll be exchanging portions of each other's samples so that we can maximize the science. The two sampling approaches are actually pretty different between Hayabusa 2 and OSIRIS-REx. Hayabusa 2 took an approach where in their first attempt, they fired a projectile at the surface and then were able to capture some of the material that was disturbed. We believe a very successful attempt, and they expect to bring back material, but we do expect, our hope is that with OSIRIS-REx, we'll be collecting significantly more mass of sample. So between the two of them, we should have an excellent combination of samples to study.
Our next question is from Marcia Dunn with AP. Go ahead, your line is now open.
Yes, hi, thank you. An operational question or two. When will you start spinning the spacecraft to see how much material was collected, if material was collected? I'm wondering, when is the soonest we might know that to get a rough idea of how much was gathered? And all the times that you gave for tomorrow, I'm assuming that's 18 and a half minutes after the events actually occur. This is confirmation times, not real time, since the asteroid's so far away. Thanks.
Yeah, this is Beth Buck. And yes, first off, the times I was saying were in the Earth reference time, so our Earth receive time. So those were already calculated and happening on the spacecraft 18 and a half minutes ahead of that. For sample mass measurement, we'll be performing that sample mass measurement, assuming everything looks good, on this Saturday, and then we'll start to get imagery back and assess what the mass differences are there, and that will be looked at through next week. So NASA and the team will be making a decision then on the 30th of this month based upon that.
Our next question is
Thomas here. From my perspective, our full expectation is that, so first of all, we recognize that our entire interests are aligned. We all want to take those samples and come home. So basically, frankly, if you looked at my schedule in detail now, you would see that there's a slot after this, for an hourly, 1 hour interaction with the team to just update on what's happening and really move forward towards that decision. A decision that we'll ultimately make together. But, if you want on the decision document, my signature is at the bottom to really go basically declare a success, which is really what we expect will be the answer of this. But needless to say, just like in all missions that we're doing, we, have fallback solutions that we already have planned, we've already thought about. But I just want to tell you, we have, worked till now with all these surprises. We've worked a really deep common understanding of our expectations. Frankly, I would be extremely surprised if this was a hard decision because of the fact that frankly, we've already talked about a lot of the scenarios, that is there. So I look forward to not only of course, tomorrow, but also the discussions that is to follow. Needless to say, this is a complex system. I'm in awe. Just take the whole measurement thing. For you teachers out there, this is one of those examples you want to use, right? How do you spin up a spacecraft that is as heavy as it is and figure out whether there's 100 grams more mass, and of course how do you do that? Using just the laws of physics. It's that simple, but it's that complex.
This is Heather Eno, so I was just going to follow up also real quick. Those instruments that I introduced earlier, they don't get to stop. So just to let you know, we will be imaging the surface with the OCAM SAMCAM instrument as we descend to the surface, to really record what's happening while we're going to the surface and backing away. And we do anticipate to be able to share some of those images with everybody late on Wednesday, October 21st, to give us the first indication of what our experience was touching the surface. So that is data that we do anticipate to share on Wednesday afternoon.
Operator, we're ready for our next question.
Our next question is from Joey Roulette with Reuters. Go ahead, your line is now open.
Hey, thank you. I just wanted to follow up real quick on the timing one more time. So at 6:12 p.m. Eastern, we'll know if OSIRIS-REx has touched down on the asteroid, and then we might not know until tomorrow whether it actually has a sample. And then the second question for anybody who wants to answer, this asteroid is obviously millions and millions of miles away, and the spacecraft needs to come within a few dozen meters from this tiny spot. Can you guys just kind of like talk about what kind of a bullseye is required to pull something off like this? How challenging has this been in general terms? Thank you.
Yeah, this is Kenny. I can confirm the timing in the first one. Yes, the nominal tag at 6:12 tomorrow is the Earth receive time, so it would have happened 18 minutes prior, about 18 and a half minutes prior, and it'll be a few days after that before we are able to confirm whether or not we have collected a sufficient amount of sample. In terms of the bullseye and targeting the tag site, you're right, we're very far away from Earth. We're relying on Earth assets in terms of the Deep Space Network to get radiometric data, but the vast majority of our navigation knowledge and our ability to determine where the spacecraft is relative to Bennu's surface and where it will be at any particular time and eventually bring us down to the surface is really dependent on the images that we take, that the spacecraft takes itself, those in situ measurements, and comparing that to detailed topographic maps that we've built over the course of the mission. And that really enables our precision to meter and even centimeter level orbit determination and orbit prediction. And that's a big, a necessary capability for us to be able to get within 7 meters or so of the tag site at touchdown tomorrow.
Questions, operator?
Our next question comes from Nell Greenfield-Boyce with NPR. Go ahead, your line is now open.
Yes, so the first question is for Beth Buck. If you could please tell me what will be your maximum moment of terror, so your moment of maximum terror during this descent. And then the other question is for Heather Enos. Let's say you get a sample, it's successful. Could you just describe in a very specific way what it would look like? Are we talking about pebbles, dust? Is it going to be gray? Like in your wildest dreams, if you got just what you want, what would it look like when you opened it back on Earth? Thank you.
I don't think I turned my mic. I just realized my mic might not have been on. Did you actually hear that?
Operator, were you able to hear Beth Buck's response?
No.
Okay. We'll begin again.
All right, my apologies. I was just saying that I'm not thinking of this as 7 minutes of terror. That's much more like a Mars EDL, an entry, descent, and landing. This is much more of a 4.5 hours of mild anxiousness. We have practiced and rehearsed with the spacecraft going through both the checkpoint burn and the match point burn. So we've seen almost all of this already, and this spacecraft is performing excellently. I really think that it'll just be a matter of what can Bunu do for us that we will actually go and touch this, so that the last little bit of this portion performs well. So I really have high confidence, and I'm just looking forward to, not with the tight stomach that I might be during an EDL, but more just looking forward to actually proving we tagged and celebrating with the team.
Thanks, Beth. So you asked, this is Heather Enos, you asked what would be the perfect sample that we would collect. And I can tell you, I have had some wild dreams, so I can tell you my wildest dream. In all sincerity, the best outcome would be that we would collect a massive sample. I mean, we say we have a requirement of 60 grams or 2 ounces, but we have the capability of collecting up to 2 kilograms, and I would love for that capsule to be completely full. And in terms of its composition, obviously we want something that represents Bennu signatures of carbon-rich and hydrated minerals, so that would be amazing, and I have every reason to believe that that's going to be in that sample. In terms of its size of distribution, I would hope that we have a couple of different sizes of distribution. I would love tiny grains. I would like a couple that are almost at the maximum 2 centimeters that we can ingest. So diversity is the key to being able to get the most out of that sample. So that is what I am, it's what my money's on tomorrow.
Heather, do you mind if I add something to it?
I don't
push,
know.
Push back on me. This is not my specialty, it's yours. But, I read the papers that just came out in Science, and I just think it's, first of all, just amazing how much science is already coming out before we even have the sample. So I just want to stop there. But one of the results that came there out of one of these papers is really focused on kind of how kind of the mechanical structure of this. And I would just want to stand back, so often we think of these samples coming back, they look a little bit like these meteorites. And I just want to say that is not the case here. If we took a rock of the type that we think and what these papers describe and kind of tossed them into the Earth atmosphere, it would not make it to the ground. If you want, the material is too brittle. Perhaps that's the right word. Perhaps there's another one you prefer, Heather. But kind of the point is, it really think of it much more kind of as kind of coming together, kind of sticking to each other. I don't know what the analog you would use on Earth, as opposed to a rock, kind of a rock that you pick up and throw into the water and makes a big splash, right? It has a different feel to it. How would you talk about it, Heather?
So I agree with you, Thomas, and that's actually one of the greatest discoveries I think we've made on the surface so far. Is we talk about this surprise of the material of not having the sandy beach, and that in itself has been a discovery that we're all very proud of. Is that we had ground-based data that gave us a good indicator based on what we call thermal inertia, or how the temperature changes from day to night on the surface, that led us to believe that we had all of this sandy beach. And by the images that we see, we can see we have these large boulders all across the surface. And what we have found, as you're indicating, is that a lot of those boulders are actually very weak and very porous. And that really is why we believe the thermal inertia still is low compared to very fine-grained material. So that in itself is something we want to continue to follow up on when we get that sample back to Earth and be able to really understand that phenomenon of its own. So, yeah, if we could bring back one of the gigantic boulders, sure, but I don't think that's going to be possible. So we'll have to make do with the 2 kilograms that's in my wildest dreams.
Operator, we're ready for the next question.
Our next question comes from Keith Cowing with NASAWatch.com. Go ahead, your line is now open.
Hi, question for Thomas, and I'm going to re-ask a portion of a question that I asked Lori Glaze earlier. NASA is going to be doing something that's never done before, with an applicability to many future missions and activities in space, the sort of things that have been called out in the Artemis Accords. And many of the missions you are sending out are technology demonstrators. If you're sending a thing to a world with a specific task of demonstrating a new way to do something on that world, then the results and the way that you got them are of equal importance, and the Accords would seem to want you to make a lot of that information accessible. Is NASA going to make the OSIRIS-REx technology available in an open source fashion for other agencies and perhaps companies to use? You know, I know there's a difference between science results and engineering performance, and there's always ITAR issues, but how is the dissemination of this new technology going to evolve?
Hey, I really thank you for the question, Keith. And of course, you know that at NASA, we have been a leader internationally in making things public. All of our data are public. And you also know, and we've communicated, that we're in a process of, in fact, also making models public because we believe so passionately in the overall dissemination of the science we do, not only because of the fact that that speeds up discovery and broadens discovery, but also because it actually inspires. We find so often that people figure out what to do with our science kind of in a ways we would have never figured out, and we have ample stories to back that up. Relative to the technologies, of course, I think there's multiple solutions that we have in mind and different approaches. In this case, the way this occurred, like just take the sample arm, it's actually invented by a Lockheed employee, and just by U.S. law, that's the Lockheed employees and then the company's intellectual property. Now, I did talk to the vice president here and basically said, if somebody was interested in that, what should they do? And they said, hey, just contact Lockheed. We're really interested in spreading that, you know. And so for us, I think there's different avenues that people could use to spread it. Just like in some of these, there's a lot of discussions right now on pharmaceutics and so forth. We know that intellectual property in many cases that is an important ingredient for the speed of pharmaceutical discovery. So if we really want speed of discovery to be the critical overlay, I think the IP model we're using is going to adapt the way it is. So I think I answered the question overall, Keith, but also answered in the context of this particular sample head. The final statement I'm going to make, the success for us at NASA is not only that these missions are being successful, but also that, frankly, any company, whether that company is called SpaceX, the United Launch Alliance, whether that company is Lockheed Martin, or any other startup, can use that technology that we help develop and actually enhance the business space that actually creates more jobs around the country and beyond. That is in the interest of all of us. So yes, we're consistent with the overall spirit of the Accords, and I think the approach that we're using is very much consistent with it.
Great, thank you. Operator, we're ready for the next question.
Our next question is from Leo Enright with Irish Television. Go ahead, your line is now open.
Thanks very much for doing this. I have a planetary protection question, so it's a bit broader. I'm just wondering what you have learned at Bennu that changes your views of the impact of asteroids such as this if they were to impact Earth. I'm not trying to portray Bennu as some kind of planet killer, but is there something we've learned from this rubble that suggests that actually a lot of these asteroids aren't as dangerous as they might be?
Hi, Leo. This is Lori Glaze, and I think that what you're referring to is planetary defense, where we are learning a great deal at Bennu about the asteroid in particular, this particular asteroid. Learning a lot more about its composition, about, as Heather was just talking about, how it's held together, the material properties, the fact that the material there is much more porous. We're also, of course, learning a lot about the orbit and the trajectory, and that's probably the most critical piece of information that we need in order to make sure that we can more accurately predict when and if Bennu will actually cross Earth's orbit at a time when Earth is in that position. As we know right now, there's about a 1 in 2,700 chance that Bennu would impact Earth in the late 2100s, about between 2175 and 2199. And so we're learning a lot from OSIRIS-REx right now that'll help us better predict when Bennu might potentially impact Earth. I hope that answers your question.
Do you mind if I add to that, Lori? And that is that if you look at the biggest uncertainties of a given rock hitting us, there's really two big uncertainties that are the biggest lead. The first one is the perturbations of the big rocks in the asteroid belt. And so, yes, we see they're big rocks there, but we need to know what the masses really are to actually know how they pull and distort in that direction. That turns out to be a big perturbation. The second one is the Yarkovsky effect, which is the effect that basically says how, the absorption from the solar light and the re-radiation after thermal transport in the body, how that kind of has, in its net effect, affects the orbit. That effect, that error bar, so to say, is really important for many of the bodies, but especially for Bennu. So my full expectation will be, as the team goes forward, and you already saw actually, again, in these science papers, that the team has done a really amazing job actually kind of nailing down the thermal transport, which is really a key ingredient to that effect. And what that will do, both for Bennu, but also by analogy to other bodies, it will, if you want, reduce the error bars that kind of are then being used to actually calculate a threat number for a given body hitting Earth. So I just want to say, kind of overall, kind of what Laura said, of course, is extremely important, but my point is the overall fundamental physics of some of these impacts are really still being learned on, and I think Bennu is going to be a really important body for us to kind of learn from for all or for many other objects such as Bennu.
Operator, next question, please.
Our next question comes from Michael Greshko with National Geographic. Go ahead, your line is now open.
Hi, thanks so much for doing this, and apologies if this is a repeat of an earlier question. This is for, I think, Kenneth, but for everyone. Bennu, being as small as it is, it's such a low-gravity environment, even small forces such as solar radiation, et cetera, can affect the orbit of OSIRIS-REx. Could you walk us through, how you all addressed those challenges as they came up, whether it was through modeling or updating orbital data or, imaging Bennu's surface to kind of figure out where the spacecraft was? Thanks.
Yeah, that's a great question. I think you're on the right track. For each of these forces that are important, and as you mentioned at Bennu, the relatively low gravitational attraction. If you look at the relative magnitudes of some of these other forces, solar radiation pressure, non-spherical gravity of Bennu itself, thermal radiation and re-radiation from the spacecraft and from Bennu itself, all of these forces, when you think about an Earth spacecraft or a spacecraft around Mars, they're important to consider, but they're more of a perturbation. When you're talking about orbiting around Bennu, they are a significant contribution to the spacecraft's motion. So we have pretty good models of those effects and how to model them. The key thing with OSIRIS-REx was calibrating those models and characterizing them and estimating the various input parameters to those models to match the data that we're seeing from the spacecraft. So as we're orbiting around Bennu, we're getting really precise measurements relative to the surface from the images and the landmarks that are contained in those images, and we're able to figure out where the spacecraft is to very high precision at any point in the past. And we're able to use that information to tweak our models until our trajectory predictions start to match what we're actually seeing in the data. And we spent, the better part of the last 2 years calibrating all of those models and really getting our navigation performance to a level that would allow us to perform tag on this rough surface.
Thank you.
Operator, we'll take our final question.
Our final question comes from Christina Anderson with AWPS News. Go ahead, your line is now open.
Thank you for taking my question. I wonder if you could talk a little bit about the students' contribution to the mission and how that has enhanced the mission and the value of that. Thank you.
Sure. This is Heather Enos, and take off my mask. I'll speak to that. I brought up the student contribution of the REXUS instrument, which is the X-ray spectrometer that was designed, built, and operated by the team of students at MIT Harvard. And I think one of the most beautiful things about that particular participation is we actually included that team in what I would call an end-to-end process. And they submitted a proposal, they designed an instrument, they built an instrument, and they've operated the instrument. And from a student participation, I would say having that opportunity on such an amazing mission is a very unique opportunity. And I personally have worked with a lot of those students and side by side with them, and just watching them grow and learn and be part of a team and problem solving, I'll say it's very beneficial to them, but I'm going to be selfish and tell you I also get a lot of personal satisfaction out of those relationships. So that's only one small, I mean, it's a large portion, but this mission has employed hundreds of students, both undergraduate and graduate students from multiple disciplines, from the very beginning of this mission to planning it, to designing it, build. I mean, I can give you some examples. The instrument teams, particularly the OCAMS team, included a lot of mechanical and electrical engineers. They participated in what we call thermal vac testing in the laboratories, just hands-on experiences that are very, very hard to come by, and this has been an excellent training ground for that. And then we went on to operations, and we have a lot of participation from students that have helped us pour through what I describe as hundreds of images, and I'm not exaggerating. They were hundreds and thousands of images, and we were proud to call them our rock stars because we did create a team of students that helped us go through image after image and really come to the conclusion of where the best candidate sample site was to get our sample from. So I would say it's been an incredible pleasure having the opportunity to train the students along the way. And I think it's, for a lot of us on this team, it's as satisfying as actually the mission itself. So I'm pretty passionate about that part of this. So.
All right, thank you, Heather. So we want to remind everyone to tune in tomorrow for NASA's live coverage of the OSIRIS-REx sample collection event. You can watch the show live at 5 p.m. Eastern on NASA television and the agency's website. In addition, please check out the new team videos by visiting NASA on Facebook and Twitter. Wish the team good luck tomorrow. Go OSIRIS-REx. Thank you, everyone, for tuning in. Operator, this concludes today's briefing.
That concludes today's conference. Thank you for participating. You may disconnect at this time.